Section 27.3, thin film interference. So if you have light that's shining on water with a thin layer of gasoline, then because of both reflection and refraction, two different light waves will enter your eye. One will reflect off of the gasoline itself, one will refract through the gasoline, reflect off the water, and then refract and come back to your eye. And because of the extra distance traveled by the one that goes through the gasoline, there can be interference between these two waves. There can be constructive and destructive interference. So the key here is we're going to focus on this gasoline that has some thickness T. That's going to be the focus of a lot of our studies. And one important detail in this is that the wavelength of the light itself actually changes as it goes from air into a new medium. So the wavelength of light within the film, like within the film of gasoline, is the wavelength of the light in a vacuum, which is just what it will be in air, divided by n, divided by that index of refraction value. So note, in air, that would be divided by 1, so that disappears. But in gasoline, the wavelength is now whatever it is normally, divided by 1.4. So that'll be an extra step to remember to include when problem solving. Now, before we can get to our full condition for understanding when we'll get constructive or destructive interference entering the eye, we need to know a little bit more about what happens when the light reflects off of these various surfaces, because it turns out that can also change things. So we're going to take a look back at chapter 17.5, looking at transverse standing waves. So from this section, we didn't, at what happens when a wave reflects off of a boundary. So if you have a pulse like on a string, you can wiggle your string up and down. If it reaches the end of the string, it will invert or go up, down instead of up if it reflects off of a fixed end, like what's shown here. So if you hold one end of the string and it comes towards you, and if it's a positive coming towards you, whoop, it flips and it becomes a trough going away. Interestingly, a pulse doesn't invert if it's a free end. If the end is able to go up and down with it, it'll keep going up and it'll bounce back with that same orientation of the up wave. So this works with a string with a fixed end and a free end. It also works for the second one, moving in a less dense medium and reflects off a more dense medium, or a more dense medium and reflects off a less dense medium. So the less dense medium reflecting off a more dense medium, we can imagine instead the string, instead of being fixed, the string is attached to a thicker rope, and it will follow the same pattern, which is what's shown in this animation. So we have the string, it approaches this boundary with a thicker rope, and the reflection is now inverted. Notice some of the wave does still transfer on through, but we're focused here on the reflection and how it inverts. In the lower one, if we start with a thicker string and it goes to a thinner one, that thinner one isn't going to be enough to clamp the string down. It's like a free end, and so the reflection will stay upright. It does not invert. Now, why does this matter? Well, this gives us a visualization of what happens with reflection off of various refractive index materials. So for instance, if the pulse or the light wave is moving in a lower refractive index material and reflects off a higher refractive index, then it is going to invert. There's going to be this phase change by half of a wavelength to go from up to down. But if it reflects off of from a higher refractive index material and reflects off a lower refractive index material, it doesn't invert. It keeps the same orientation. So this is the picture I want you to hold in your mind. I find these GIFs really useful to be able to see a little more of what's going on here. So here's how our book describes it for section 27.3. When light travels through a material with a smaller refractive index towards a material with a larger refractive index, reflection at the boundary occurs with a phase change. It's equivalent to 1/2 of a wavelength in the film. And that's what's shown here with the hard boundary, that the incident wave, when it reflects, whoop, becomes inverted, the opposite. On the flip side, when light travels from a larger toward a smaller refractive index, there's no phase change upon reflection. So the main thing here is this is going to be something you have to observe in a problem where you're going, okay, the light is here reflecting from one to another. Is there a phase change? And if so, then you record it. And if not, then you don't have to add that into your equation. So let's look at an example of this. A colored thin film of gasoline. A thin film of gasoline floats on a puddle of water. Sunlight falls perpendicularly on the film and reflects into your eyes. The film has a yellow hue because destructive interference eliminates the color of blue from the reflected light. The refractive indices of the blue light in gasoline and water are 1.4 and 1.33. Determine the minimum non-zero thickness of the film. Okay, so notice we have the same picture that we had looked at briefly before, that we have light that's reflecting off of the surface of the gasoline coming to our eyes. That's pretty straightforward. It's all in the air. It's very simple. Some of the light goes through the gasoline and reflects off of the water to then come to our eyes, and it goes through that thickness T. So let's see how we can put all of that information that we've been learning together here. So the key is we want to find the total path difference and phase change. So first, the path difference is how much longer is path 2 to path 1? Well, it's quite literally just the distance t times 2. So it goes in the thickness and out the thickness, 2t. That one is always the same, so that's a nice consistent path difference. The other thing that we'll need to account for, though, is any phase change in the reflection. So let's check if the air is reflecting off the gasoline, it's a lower refractive index reflecting off of a higher one. So this is like the light string on the heavy. And so this is one where it is going to invert. This is going to be a phase change by half of a wavelength. Notice for the gasoline, it's reflecting off of the water. So this is the heavy rope with a lighter rope. This is not going to invert it. So this will keep the same orientation. That means one of them has flipped, but the other hasn't. So the net phase change is half of a wavelength. If they both flipped by half of a wavelength, then there'd be no net phase change. We wouldn't need this half of a wavelength. But as it is, 2 is out of phase of 1 by half of a wavelength. So we add that in to account for that. And then finally, we set the net change in path difference and phase change equal to whatever our condition is for constructive or destructive interference, depending on which one we want to focus on here. So the problem said we want to find destructive interference for blue light. So I'm going to use my destructive interference condition, which is that the path length difference and the phase change has to be equal to half integer wavelengths. So half of a wavelength, 3 halves of a wavelength, 5 halves of a wavelength. One other thing to note here is that all of these wavelengths aren't just our normal lambda. They're wavelength sub-film. Why is that? Well, remember, with any thin film interference problem, we're focused on how the light has to pass through this film. And so all of the wavelengths will have to be lambda film, which will be an extra step. So the minimum non-zero thickness. Well, let's see. So if we start with 1/2 of a wavelength first. So we choose this. Well, then if we subtract our 1/2 lambda over there, we'd get 2t is equal to 0. Or the thickness is equal to 0. And that's not a non-zero thickness. So that doesn't work, right? But we could try another one. So we could say, okay, let's try a slightly larger path length difference, 3 halves lambda with the 1/2 lambda film and 2t. So if we subtract the 1/2 lambda film over there, then we get 2t is equal to something that is non-zero. 3 halves minus 1/2 is just 1. So it's just equal to, this lambda film. Yeah, and that would have it right there. But if we want to solve for t, we can divide both sides by 2. And so we get T is equal to lambda film over 2. Now, the other way to approach it is the way that they did here, and they just said, hey, we don't know what m value we want to use, so we'll leave it in terms of m for now. That works just as well, because then you get a condition for t, and you can see, okay, if I plug in m equals 0, I'll just get a thickness of 0. If I plug in m equals 1, that'll be the smallest thickness that's non-zero. And that's indeed what they did here. So they said m equals 1 as opposed to m equals 0. Notice for lambda film, it's our wavelength divided by the 1.4. We need to include that still. And they find the thickness of the gasoline is 168 nanometers. So very thin, but enough to produce this effect, to destructively interfere for the blue light, but not for the yellow light. Right, so conceptual example, multicolored thin films. Under natural conditions, thin films like gasoline on water or like the soap bubble shown in the figure, they have this multicolored appearance that often changes while you're watching it. Why are they multicolored and why do they change with time? Well, the key here is like with this soap bubble, is the bubble doesn't have a uniform thickness. Right? Parts of it are thicker or thinner, or even have soap in there to make it thicker or thinner. And that changes with time as the water starts to evaporate. Or it can even just be shifting around. And so you see this amazing rainbow effect. And this is something I encourage you to look around, because sometimes you can see it in your everyday life. So here's an example at, the Estero, right by Dennis the Menace Park in the background there, and you can see this rainbowing effect in the water. So I'm not sure what was in the water, hopefully not gasoline, but there was something in the water that was a separate thin film from the water and producing this cool interference effect. So we can at least get excited about the science, and perhaps that's cause for environmental concern or investigation. Interestingly, you can get this effect just by having air as your thin film. So there's a wedge of air formed between two glass plates, where the plates are just offset by a sheet of paper. That's super thin, right? But that's enough that the light could come in and go through the glass and reflect off of that air boundary, as well as reflect off of the lower glass boundary. Notice for this one, we might as well check it while we're doing this. If we're reflecting from the glass to the air, that's reflecting off of a lower refractive index, so this one will not invert. But for path 2, it's going from the air reflecting off the glass, the heavier ones, this one will invert, so the net phase change will still be half of a wavelength as before. Another way you could observe this is if you just have a spherical piece of glass, like a lens, and you put it just on a flat surface. You will see rings around it that are multicolored due to this interference, and the interference is slightly different for the different wavelengths of light. So this is amazing to see. It's a real effect. So in summary, remember the wavelength of light in a film is different than in a vacuum or in air. You have to divide by n, that refractive index. We also have this reflection phase change, which if you're reflecting off of a higher end material, the phase change is half a wavelength in the film. If it's off a lower end material, there's no phase change. If they're both a phase change of half a wavelength, the net change would still be 0. The path length difference we saw is always 2t, and it's equal to our condition for constructive or destructive interference, either m lambda or m plus 1/2 lambda. So that's a handy synopsis of it. One last application of all this, 27.4, the Michelson interferometer. This is a device that's used that takes advantage of interference, where there's a light source and a beam splitter. So part of the beam reflects off of this and goes to an adjustable mirror, while another part passes through, goes to a fixed mirror. And you can make fine-tuned adjustments to the adjustable mirror to get constructive or destructive interference. And that is one of the ways that the speed of light was determined. This was done over very great distances. So, cool application there, and we will wrap up right there.